This video is about the exceptions to the octet. You should already be able to draw Lewis structures for compounds that do abide the octet rule from year 1 and identify their shape and polarity. But by the end of this video, you'll also be drawing Lewis structures for compounds that disobey the octet to identify their polarity and identify which elements can be electron deficient and which can exceed that octet and why. So first, question of the video, how on earth do these exist? Because these are not things that we talked about in year 1. Like, how do we get things that are not tetrahedral, that have way too many things bonded to them? So there's exceptions to the octet rule. The first exception is that boron tends to form compounds with incomplete octets. It may have only 6 electrons. And the reason for that is that boron is almost semi-metallic, right? It's on the staircase. It has very much tendency to behave covalently by sharing its electrons, but it only has 3 electrons to share. And because it only has 3 electrons to share, it will only give 1 to each bond, and then the element that it's bonding with, like hydrogen, will only give 1 to the bond as well. So this will only constitute 6 electrons total. And that's okay for now. And aluminum might do something similar, although we might consider aluminum to be more metallic and therefore might probably behave more ionically, where aluminum would be +3 and each chlorine would be -1 and not share but transfer electrons. But sometimes you do see it like this. So that metalloid, semi-metal type properties are letting it be under the octet, not have an 8. The second exception to the octet rule is that some elements can exceed the octet when needed. So not all the time, just when needed. Only elements that have an open d orbital can do this, which means periods 3 through 7, elements in periods 3 through 7. And again, we're talking about covalent bonds right now, so this is nonmetals only. Nonmetals elements 3 through 7. So it's not actually that many if you think of it. Let's talk about the reasoning why. I'm going to talk about phosphorus. Phosphorus normally looks like this configuration: 1s2, 2s2, 2p6, 3s2, 3p3. Phosphorus would like to obtain 3 more electrons in order to fill its octet. So it might do that by becoming PCl3. Each of those chlorines is going to share an electron with phosphorus, filling in the extra orbitals. But when you start doing that, you're actually opening up a 3d orbital as well. When you open up 3s and 3p, it's almost like you're opening up the whole level. 3d is open, it's just not filled. So it's sitting out like this as PCl3. The reason PCl5 might occur is because these extra electrons from these extra 2 chlorines might start filling up a 3d level. So that's why I was saying that they need to have open d orbitals and they need to be in levels 3 through 7 because there's no such thing as 2d or 1d levels. So those elements in that section, like boron through neon or silicon through, boron through neon or helium, they just don't have the ability to have this d level open to fill electrons. So the general rules for this exceeding the octet thing is that an atom will bond as many times as it needs to fill its octet. So we saw phosphorus had 5 valence. It should only have bonded 3 times to fill its octet, and that's where we stopped last year. But if there's an abundance of reactants under high pressure, the atom may bond as many times as it has valence electrons. So in the previous example, phosphorus had 5 valence electrons, so it could bind up to 5 times, right? And that's why we saw in the previous example it had those 5 bonds. Sulfur is the same way. So sulfur has 6 valence electrons. It might only need to bond twice. This would be under normal conditions. But if there's an abundance of fluorine under high pressure, the fluorine might now, because it's so electronegative, attract into those extra electrons. And it can bond 4 or as many as 6 times because sulfur has 6 electrons to share. So for each electron it has, it can share that electron. And those electrons are going into its d orbitals. So let's try to draw some of these examples out. You're going to put your least common element in the middle. The more common element, like fluorine, around the outside as symmetrically as possible for now. And if there's any extra electrons, put them on the central atom. Maybe pause the video and sketch through what you think they might look like. Alright, so ClF3. The chlorine's going to go in the middle. The fluorines are going to be on the outside as symmetrically as possible. If you had them more spread out, that's fine. And then any extra electrons, remember you have to add these up first. There are 7 electrons in each chlorine and fluorine for a total of 28 electrons. So when you first drew it, you had 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. The extra 4 electrons go on the chlorine. This shows that chlorine could have bonded a couple more times, up to 7, but it just didn't yet. This is an abnormal because chlorine should have only bonded the 1 time. In XeO3, I know Xe shouldn't have had a bonded at all, right? Xe is a noble gas, it has 8 valence, it's stable. But in the abundance of oxygen, where oxygen is under high pressure, the oxygen is also extremely electronegative. It can force xenon to react. also because xenon is so big, it's not very good at watching its valence electrons. So in that case, I drew a xenon a couple of ways, and you can have any modification of this, where xenon's in the center, oxygens are on the outside, whether it's top, side, bottom, I don't care, and then the electrons around. Most of you probably drew it with single bonds, where there's going to be 2 electrons per bond, and then each oxygen would need 6 more electrons to get an octet, and the excess electrons go on xenon. Why? Because again, if you count your electrons ahead of time, you would have 8 from xenon and 6 from each oxygen, and you need to show all those. All these dots might be oxygen 6 electrons. All those are oxygen 6, oxygen 6. This bond must be made out of xenon's electrons only. Oxygen stole both electrons from xenon and these two for 6 electrons and 2 extra that it didn't steal yet. That means that it's ready for another oxygen to come in and steal its electrons, basically. Right? I also showed it here as double bonds because that would actually also work. And any in between of that, like you can have a double and a single, 2 singles, or 2 singles and 2 doubles and 1 single. And we're going to get to that in the next video, but I'm just saying that there's probably more than one answer. In BCl3, remember boron is under the octet, so boron will only bond 3 times because it only has 3 valence. So it's okay that it doesn't have the dots on the top. You cannot put them there. They don't exist. Boron had 3 valence electrons. Each chlorine had 7 for a total of 24. You can only show 24. You can't show 26 electrons. In I3-, you need to know that that negative means it has an extra electron. In that case, I would have 21 electrons if I didn't think of it, which doesn't make sense because we usually pair electrons together. So it has 22 electrons to show. I'm going to just put iodines in a row and give them 2 electrons. Remember, the bonds can be shown as lines or dots, so this one's showing them as dots. These 2 electrons between the 2 iodines are shared. Same thing here. So we have 2, 4, 6, 8 around that one, 2, 4, 6, 8 around this one, 16, 18, 22. Right? So all those extra electrons are going in the central atom I. And again, we're taught this more in class, but the reasoning being that iodine came with 7. 1 for each iodine that it's bonding to, and then this original other 5. 1, 2, 3, 4, 5, 6, because there's an extra electron. Let's do it one more time. ACl4. I is going to go in the middle. Chlorine's around the outside with an extra electron, because right now it would only have 35 electrons. That negative gives us a 36th even number. Iodine in the middle, chlorine's around the outside. A lot of people probably, again, miss those extra electrons. But if you count them up and have 36 electrons, it would be 2 per bond, that's 8. 10, 12, 14, 16, 18, 22, 24, 26, 28, 32 around the chlorines. I need to show 36. So those 2 extra pairs need to be on the iodine. Why? Because iodine originally had 7. 1 per bond, 1, 2, 3, 4. And then all the extras on the outside, 5, 6, 7, and then this extra negative, 8. We'll be practicing this in class. We'll also construct models. It'll make it a little easier. But for now, keep in some rules in your head, which were that elements have open d orbitals can exceed. This is what exceeding looks like, where there's extra electrons on the central atom, that the outside electrons always obey the octet. And a polarity reminder that electrons, the element that's more electronegative will pull electrons towards it to create a dipole moment, where it's more negative than the other side that's more positive. And you can show it in 2 different ways. So this will also happen to the things that exceed. And we showed that with arrows, right? So if chlorine's more electronegative, the arrow went towards the chlorine. Or if oxygen's more electronegative, it brings it down towards oxygen. So this can happen with the more complex things, like sulfur hexafluoride we saw before. There's going to be electrons being pulled in every direction by every fluorine. That means this is completely symmetrical, even though we don't know its shape yet, because there's fluorine pulling in every direction. And that symmetry means it's not polar. At this point, you should be able to try to draw Lewis structures for any compound ever, and identify if they're going to be octet deficient or if they're going to exceed the octet and why.